This will be an in-depth lesson on material performance indices. In particular, we'll focus on what they mean, how to calculate them, and how to use them to select the most suitable material. When selecting materials, performance indices are the tool that allows you to rank materials according to how well they meet a project's objectives. These indices are generally expressed in terms of material properties and can come in two different forms. In the simplest case, the performance index matches a single property, for example, when the requirement is for the material to be as stiff as possible. The typical situation is when the objective is independent of constraints, meaning when a material property needs to be maximized or minimized without any particular implications regarding the constraints to be met. In the second case, however, the constraints to be met and the objectives to be achieved are linked together through geometric variables, such as the thickness or the cross-section of the product. In this case, the performance index becomes a combination of several properties. For example, this happens when a product is required to be sufficiently strong to minimize its mass and to have as large a cross-section as desired. To meet the strength constraint, one could choose strong materials or larger cross-sections. To reduce the mass, on the other hand, the focus will be on materials with low density or smaller cross-sections. The possibility of using the cross-section as a design variable creates the link between constraints and objectives. And the result leads to indices expressed as a combined function of several material properties. This means that, in addition to the objectives, the constraints, the free variables, and the very function of the product itself all contribute to identifying the specific performance index of the material. Or, in other words, the project translation, in which all these parameters are described. Gathering and specifying them is the first step to take in order to formulate the performance indices, which are then used to evaluate the best material for making a specific product. Since the use of performance indices is essential for optimal material selection, in this lesson we'll take a closer look at how to determine a specific index for a given project, and we'll do so by considering a project where stiffness is the main factor. This means that in our examples, the stiffness of the product will be the main constraint of the project. The stiffness of a product can be defined as the ratio between an applied force and the resulting displacement. In other words, if a product is subjected to a certain force F, it cannot deform or stretch more than a certain amount delta. Depending on the type of product, stiffness will take on a different form. In fact, it's not the same thing to talk about stiffness in tension, bending, shear, or compression. Specifying how the product works relates to its function. Alongside these variables, we then need to specify the objectives we want to achieve, such as minimizing mass, costs, and overall size, as well as the free variables left to the project design, which generally involve the ability to choose from a wide range of materials or certain geometric details of the product, like its cross-section, thickness, or width. So we choose an initial trial configuration and proceed with the translation of the project. The first case is that of a bar working under tension, or a tie bar. The constraints will concern the fact that it must be sufficiently rigid and have a given length L. We will assume that the objective to pursue is minimizing the weight. Finally, we will adopt as free variables the choice of materials and the cross-section of the bar. Let's first make explicit the so-called constraint function, which for a bar under tension imposes the following relationship between the Young's modulus of the material, the cross-section A, and the length L. In this equation, we've highlighted the free variables in red, showing that to achieve a bar with the required stiffness, you can act either on the choice of material, through the Young's modulus, or on the cross-section of the piece. The equation is a well-known solution, but for those who want to trace its origin, the steps are shown in the box. We start from the concept of the stiffness of the piece as the ratio between a given force and a maximum acceptable displacement. The force can also be expressed as the product of an axial stress and the cross-section of the bar, while the displacement can be expressed as the product of the induced strain and the initial length. Finally, considering that the ratio between stress and strain in the elastic range is the Young's modulus, we arrive at the indicated formula. Now let's express the objective function, that is, the characteristic to be minimized, in our case, the mass. This parameter will also be expressed as a combination of material properties, namely the density, rho, and the geometry of the piece, that is, its length and cross-section. Here too, by highlighting the free variables in red, you can see that we could obtain the lightest bar either by choosing materials with low density or by reducing the cross-section. In these two equations, the free variables are, as their name suggests, free, but in reality, they imply certain interrelationships. On one hand, modulus and density are linked to each other since they refer to the same material. On the other hand, the cross-section can be varied as desired, as long as it allows the stiffness constraint to be met. At this point, we combine the two equations together. Let's do this to have a solution that relies entirely on the choice of material, replacing the section A expressed in the constraint function within the objective function. By carrying out the simple steps indicated, the new formulation of the function is obtained. The new formulation of the objective function consists of a first term that specifies the desired stiffness, which is therefore a constant in the problem, a second term that contains the constrained geometric variable, in this case the length of the bar, which is another constant, and a third term that is instead free and appears as a combination of the material properties. If you choose the material with the lowest value of this term, you will achieve the goal of minimizing the mass. In other words, among rods with a given stiffness S, the one with the lowest mass will be made with the material that has the lowest value of the ratio, rho over E, or the highest value of its reciprocal, that is, the Young's modulus normalized to the density, which will be the material performance index, I. This second expression of the index is generally the most widespread, because it's normal to think in terms of maximizing performance. Moreover, this particular formulation, E over rho, is a well-known term and is also known as specific stiffness. Now let's modify the design parameters one at a time, starting with the function. Let's consider the case of bending, which is one of the most important types of stress in engineering. So let's present design translation for a bending bar or beam that needs to be sufficiently stiff and have the lowest possible mass. Compared to the previous case, the change to be made to the design translation therefore only concerns the function, while constraints, objectives, and free variables remain unchanged. Just for the sake of simplicity, the constraints also specify that the cross-section of the bar is square. By changing the function, the type of stiffness to be ensured will also change. This time it will be flexural, rather than axial, and is generally defined as the ratio between the applied force and the deflection of the bar. Therefore, the formulation of the constraint will change, expressed as the product between Young's modulus and the moment of inertia, I, and divided by the length of the beam, L cubed. In this formula, on the other hand, is a constant that refers to the distribution of the force on the beam. The constraint is then reformulated, making explicit the moment of inertia for a beam with a square cross-section A. The objective function, on the other hand, remains unchanged, just like in the previous case. Now, let's proceed by substituting the section expressed in the constraint function into the objective function. This allows us to express the mass as the product of a constant term related to the function of the constrained geometry and a free term that depends only on the material, highlighted here in red. The best materials for a light and stiff bar are those with the lowest values of rho over the square root of EO, which maximize the ratio of the square root of E over rho, representing a new material performance index specific to this particular design. Referring again to the case of bending, let's change the free variables. We'll fix the width and leave the thickness free. The following example is also commonly associated with the case of a stiff and lightweight panel. The constraint and objective equations will not change, although in this case it will be the thickness, whose dependence is highlighted in the equation, that allows us to combine the two functions. By combining these two functions, we arrive at an appropriate expression for the objective function, which shows that the best materials for a stiff and lightweight beam with variable thickness are those with the lowest values of rho over the cube root of E, or that maximize the cube root of E over rho, which represents the new material performance index for this specific case. Let's change the free variables again, this time freeing the width and fixing the thickness. Following the same approach, we first make the constraint and objective functions explicit. Next, the constraint function is substituted into the objective function using the width variables. By combining the two functions, we obtain as a new index the ratio E over rho, which represents the material performance index for this type of project, and which, among other things, matches the bar under tension bar that we saw earlier. And what if we didn't have any geometric free variables, but only the choice of materials? In that case, the constraint and objective functions are no longer coupled and play two different roles. The first acts as a filter and will eliminate all materials that do not have a Young's modulus value high enough to ensure good stiffness. The second acts as the objective, and it will indicate as the best material the one that minimizes mass, that is, the one with the lowest density. The new material index is no longer a combined property, but coincides with the reciprocal of the density. As a final set of cases, let's consider what would happen if we wanted to change the objective, such as minimizing costs or minimizing bulk. Let's try to solve them in the simplest case, that is, the bar under tension we dealt with at the beginning of the problem. In both cases, the change will concern the function objective, which in the first case will be expressed as cost, that is, the product of cm, cost per unit weight, the material density rho, and the product of cross-section and length by substituting the cross-section and thus combining the constraint function. With that objective, it follows that minimizing the cost is achieved by minimizing cm times rho over E, or by maximizing its reciprocal, the new index is E over cm times rho. Now let's look at the second case, that of minimizing the bulk. In this case, the objective function will be the actual volume of the product, and the cross-section will be the only variable to adjust. By substituting the section from constraint function to objective function, we find that to minimize the volume, we need to maximize the Young's modulus, which becomes the new index for this type of project design. This is a reliable result that tells us, in fact, that to obtain products with a given stiffness and the smallest possible dimensions, we need to use the stiffest material. Now let's summarize the cases we've discussed and their corresponding indices in a table. This list allows us to reiterate that performance indices are specific functions based on the properties of materials and closely tied to the design case, particularly to the combination of function, constraints, objectives, and free variables. Many more of these indices, described for many other application cases, can be found in Professor Ashby's books. The book shown on this slide contains the most comprehensive list of them. This same book also describes how to determine the relevant indices following a specific sequence of steps. The sequence of steps involves translating the design requirements into terms of function, constraints, objectives, and free variables. State an equation for the constraints that affect the project. Develop an equation for the objective. Identify the free variables in these equations. Substitute the free variables wherever possible, starting from the constraint equation within the objective function, and identify in the new objective function the material properties, whether individual or combined, that optimize the problem. Finally, make the material index explicit. Expressed as a quantity that optimizes the performance index and serves as a criterion of excellence, the approach is simple and general, and is commented on by Professor Ashby as follows. It sounds easy, and it is, as long as it's clear from the start what the constraints are, what you're trying to maximize or minimize, which parameters are specified, and which are free. But once we have these performance indices, how are they applied in a project? If we're faced with a table of data, maybe organized in a spreadsheet, it becomes easy to calculate the index for each material and make a ranking of the best ones. The index isn't just used to rank materials from best to worst, it also lets us understand how much the first one surpasses the second one, and how much the second one surpasses the third one, and so on. Moreover, the index helps us identify materials that, even though they belong to very different families, show similar values to each other. This gives us possible alternatives in design, even very innovative ones, to make the same product. Now let's see how to use performance indices for a graphical type of selection. Indices are particularly useful and easy to apply even in bubble diagrams. In these charts, indices are indeed represented as straight lines. This happens because bubble diagrams are usually plotted with logarithmic axes. Let's take, for example, a relationship like index 1 equal to the ratio between e and rho, which can be rewritten as the log I equals to log e minus log rho, or in other words, log e equals to log rho plus log I. In a bubble diagram on a logarithmic scale, where the Young's modulus e is shown on the y-axis and the density, rho, on the x-axis, this expression describes a straight line with a slope of 1. The vertical position of the line indicates the material's performance, I. The higher the line, the better the material's properties in relation to the considered index. Applying an index graphically therefore means drawing level lines that cross the bubbles in the diagrams. These lines represent the performance of materials or their families. All materials that are on the same line have equivalent performance. Those above are better, those below are worse. The distance between the lines also tells us how much better one material performs compared to another. Now let's look at this graphical application for the other indices we've encountered in this lesson. The same reasoning applies to these ones too. We will have lines with a slope 2 in the case of a beam with variable cross-section, lines with a slope of 3 for a beam and a panel with free thickness, a vertical line when minimizing mass without free geometric variables, and a horizontal line in the case of minimizing bulk. Indeed, in many bubble diagrams available online, these lines are already drawn, because they are useful for making the interpretation and use of these graphs more immediate. These considerations on the graphical approach to material selection allow us to understand why software, such as Grunter, is particularly useful for the project design. In addition to being an important database, the software allows you to visualize material properties in graphs, interact with these graphs, modify parameters, and see in real time how certain choices affect material selection. In fact, the software allows you to set limits to immediately exclude materials that do not meet a certain requirement by directly setting threshold values, such as a maximum value for density or a minimum value for Young's modulus. Furthermore, it also allows you to graphically narrow down the area of interest, excluding materials that fall outside certain properties. You can then use the indices guidelines to isolate or broaden the selection, focusing on a smaller number of candidates. The software provides both a graphical display and a numerical ranking of the materials with the best performance. In this in-depth lesson, we saw that material performance indices are tools that allow you to identify the most suitable material. For a given application, or one that arises from a combination of function, constraints, objectives, and free variables of the project, the index can coincide with a single property, for example, stiffness or density, or with a combination of several properties obtained by combining the constraint and objective equations. By changing the objectives, such as mass, cost, or size, or the free variables like section, thickness, or width, you get different indices even for the same type of product, allowing you to adapt material selection to a wide variety of cases. The indices can be used to create numerical rankings or applied in bubble diagrams to identify the best materials for a given project by comparing their performance and narrowing down the selection to those materials that best meet a specific requirement. And software like Grant proves especially useful for this purpose.